Dear all, hello everybody. It is my pleasure today to introduce Professor Stephan Wagner from the Institute of Discrete Mathematics of Graz University, Austria. Professor Wagner is a distinguished mathematician whose research lies at the forefront of discrete mathematics. His work focuses on combinatorial probability, including the study of random trees, random graphs, and other random structures, as well as enumerative and analytic combinatorics and graph theory. Through his contributions, Professor Wagner has provided valuable insights into the intricate and fascinating world of mathematical structures, enhancing our understanding of both their theoretical foundation and practical applications. Please join me in welcoming Professor Wagner, who gives us today a talk with title Local Limits of Descent by the Permutations and the Trees. Please, you can start, Professor.
Thank you very much for the kind introduction, and thank you for having me. I will be talking about some recent joint work with Paul Thevener, who was also visiting Graz recently. It's about a probabilistic model of permutations and also trees biased by their descents. I will explain exactly what this probabilistic model entails. The The background in this lies in the study of different classes of trees, actually. So, in order to motivate the things I will be talking about, I would first like to start by introducing some specific classes of trees. The first of which is rooted labeled trees. So, in a rooted labeled tree, like the one shown here in the figure, all vertices have a unique label between 1 and n. So this particular tree has 10 vertices, and the vertices are labeled from 1 to 10. They need not be in any specific order, and the order of children also doesn't matter specifically. So if I were to switch the 4 and the 7 around here, for example, it would still be considered the same tree. I'll always draw my trees with the root on top. So the vertex labeled 5 here is the root of the tree.
Sorry, a question, please, about the previous tree.
Yes.
How you label the ages of this tree? Why 10 is at left and, for example, 2 is at right? Or at random, you give some label to...
There is no particular order in the vertices. I could draw them in any way. I could, as I said, switch the 4 and the 7 here. I could switch this entire branch against that branch over here. All that matters is the parent-children relations. So the children of vertex 5 are 1 and 9, but they are in no particular order. So I could draw this entire thing here to the left of the number 1, and it would still be considered the same tree. So they're not necessarily in any particular order.
Okay, thank you.
Right. So these are rooted labeled trees, labeled simply by uh, assigning a label to each of the vertices. They're a special case of what is known as simply generated family of trees. And these are also related to what is known as conditioned Golden-Watson trees. So they're a special case of conditioned Golden-Watson trees. In fact, if you generate random trees according to the Golden-Watson construction with a Poisson offspring distribution, then you actually end up with random rooted labeled trees if you condition on a certain number of vertices. Another important thing about these rooted labeled trees is their numbers. So it is a famous result due to Cayley that the number of labeled trees within vertices is n to the n minus 2. If I also specify a root for my vertex, that gives me another n possibilities. So n times n to the n minus 2 gives me n to the n minus 1. There are many combinatorial formulas around rooted label trees, capturing not just the total number of such trees, but also aspects of their structure, statistics, such as, for example, the number of vertices of a given degree or the degree of a specific label, many other things. So one structural feature that is important is that the height, so the greatest distance from the root to a leaf, is approximately of order square root of n for a large tree with n vertices. And the average distance from the root, as well as the average distance between two vertices randomly chosen, is of the order of magnitude square root of n. This will be in contrast to the other family of trees that I will talk about a little later. And that other family is the family of recursive trees. So recursive trees can be obtained by adding vertices step by step. Equivalently, there are rooted label trees where the labels are increasing. I'll illustrate this in an example. So I'll start with the root vertex, which is vertex number 1. Then vertex number 2 attaches to vertex 1. And in each subsequent step, one of the vertices attaches to one of the previous vertices, and that's chosen uniformly at random. So vertex 5 attaches to one of the previous 4, each of them chosen with probability 1/4, for example. So then you get a sequence like this. Vertex 3 attaches to 2, then vertex 4, vertex 5, vertex 6, and so forth. So vertex 7 now, for example, would have a probability of 1/6 to attach to any of the previous 6 vertices. So for example, it goes here. Again, the vertices are in no particular order. So the left to right order doesn't matter. It's only about the parent-child relations. So I continue this. Now I have a tree with 10 vertices. And you see that in contrast to the previous class of trees, the labels of the vertices are necessarily in increasing order. So the root always has label 1, and further vertices have labels that increase as I move away from the root. So for instance, if I go along this path, the labels increase 1, 2, 3, 9, 10, and that's the case everywhere. So the children of a vertex always have to have a greater label than the vertex itself. The recursive trees belong to a broader family of what is known as increasing trees, and they're characterized by this property that the vertex labels increase from the root to the leaves. They can be counted, and it's actually not very difficult to count them. The number of such recursive trees with n vertices would be n-1 factorial. That's because the nth vertex always has n-1 possible places to attach to. So by a simple induction, I'm getting n- factorial possibilities for the number of recursive trees. And indeed, there are nice combinatorial connections to permutations, which is suggested by this counting formula. So we can bijectively relate increasing trees with n vertices and permutations of n-1 elements, including some of their features and statistics. Now, in contrast to random rooted label trees that I mentioned previously, these have a somewhat different shape. They're flatter and wider in some sense. The height is of orders logarithm n, and the average distance from the root is also of asymptotic order logarithm of n. That's in contrast to the square root n regime that we had for rooted label trees. Now, the thing that we were motivated by was to produce some probabilistic model that could interpolate between the two. So you want something that's somehow in between rooted label trees and increasing recursive trees. And we do this by associating a weight with each label tree that is based on the number of what we call descents. So a descent in a tree is a pair of parent and child with the property that the parent label is greater than the child label. Now, a recursive tree has the property that there are no such descents, right? The way these were constructed, the parent label was always less than the child label. So this particular inequality would never occur in a recursive tree. And currently, a recursive tree has 0 descents. A random, or not even random, a rooted label tree, on the other hand, can have any number of descents, really. So in the example of the rooted label tree that I showed you earlier, there are 4 descents in total that are formed by the vertex pairs 5, 1, 9, 2, 6, 3, and 10, 6. So these are the edges where the labels are sort of in reversed order. Right. So a rooted label tree can have any number of descents between 0 and number of edges, which is n minus 1, whereas a recursive tree has no descents whatsoever. So we interpolate now between these two by introducing a weight, and for this weight we need some parameter q, positive real number. And we consider a probabilistic model where random rooted label trees are generated, but not with uniform probabilities, but with probabilities that are proportional to the quantity q to the number of descents. So in particular, when q is 1, then the probabilities are proportional to 1, so they are all equal. In which case, I'm just get uniformly rooted label trees, uniformly random. If, on the other hand, I let q go to 0, then eventually only trees with without any descents will be generated because the others have such a small probability. So in the limit as q goes to 0, I will end up with random recursive trees. The parameter q here is allowed to depend on n. Now, this kind of probabilistic model is very common, especially in the context of statistical physics, where I generate states of some system according to probabilities that are proportional to a quantity like this. And the number q here then in the physical context is related to the temperature of the system. But I will not go into depth there. Should just be said that this kind of probabilistic model is indeed quite common, where you take some structure and generate it with a probability that's proportional to q to the power some statistics of the system. Now, importantly, the parameter q here is in principle allowed to depend on n as well. Now, a first question one might ask is about enumeration of such trees. So can I actually count how many labeled trees have a specific number of descents? And this has actually been done quite some time ago. So in a paper from about 40 years ago by Yoglu and Remmer, the Q enumeration of labeled trees by the number of descents was already studied. So they obtained generating functions and some counting formulas allowing you to get the number of rooted labeled trees with a certain number of descents as well. And what I said before is that this model does exactly what I wanted to do what I outlined before. It interpolates between random rooted labeled trees, which occur when Q is 1. Then all the probabilities are equal. And in the limit as Q goes to 0, I obtain random recursive trees because then um, anything with a positive number of descents will have negligible probability as Q goes to 0. And conversely, if let Q go to infinity, then only trees with maximum number of descents will survive. So I will get random recursive trees, but with labels reversed. So then the largest label n would be at the root, and the labels would decrease as I move away from the root. Now, the fact that Q going to 0 and Q going to infinity are basically the same model has a generalization. So if I replace Q by 1 over Q, that amounts to just reversing all the labels. So I replace 1 by n, 2 by n minus 1, and so forth. So if I only care about the shape of the trees, then really I need not distinguish between the parameter value Q and the parameter value 1 over Q. So it's good enough for us to consider Q less than or equal to 1 in the following. All right, so before I'm getting to actual results about this probabilistic model, I want to also introduce a related probabilistic model on permutations. So for permutations, I can also define what a descent is. It's simply two consecutive numbers in my permutation where the first is larger than the second. So where I'm going down, so to say, in the permutation. And again, I can consider random permutations where the probabilities are proportional to Q to the number of descents. So for example, in this permutation here, the descents are 8, 2, 9, 7, and 7, 1. So there are 3 descents in total. And again, a permutation of n elements can have any number from 0 to n minus 1 descents. So once again, I introduce a bias based on the number of descents. If I make Q very small, then the permutations are biased towards having very few descents. If I make Q large, let Q go to infinity, then the permutations will be biased towards having lots of descents. So in the limit Q going to 0, I'm just getting the identity permutation 1, 2, 3, 4, 5, and so on. And as Q goes to infinity, I'm just always getting the reverse permutation in n minus 1 and so on. A little bit of combinatorics around this. Permutations with a certain number of descents are very well understood. So they're counted by a classical number array known as the Eulerian numbers. They are somewhat similar to binomial coefficients, Stirling numbers, and so on. They form an array satisfying a similar recursion. The Eulerian polynomial that has these coefficients as its coefficients can be expressed quite nicely like this. So counting these permutations is something that's rather well understood. Now we would like to go and turn this into a probabilistic model by, as I said, picking these permutations with probabilities proportional to this quantity Q to the number of descents. There are similar models of random permutations following a very similar definition, except that I'm replacing number of descents here by something else. The two classical models in this regard are Mallow's permutations, where instead of descents, I'm taking the number of inversions, and Ewan's permutations, where I'm taking the number of cycles here. So in each case, I'm introducing some bias on permutations and generate permutations with these biased probabilities. So now what's the connection between permutations and trees? So why do I need permutations to study trees? Or maybe why would I naturally be interested in permutations if I want to study the model of descent bias trees. So one of the connections is that I can consider the path from the root to some fixed vertex, like vertex n. Can do this with pretty much any fixed vertex. Now, if I remove the edges of this path, then my tree falls apart into smaller trees that I've tried to indicate by these figures here. So the somebody might need to mute themselves.
Yes, sorry.
Okay. Thank you. So the tree can be decomposed into these, so to say, butterflies, which are the components that are remaining if I remove all the edges on the path from the root to vertex n. Now, I can sort of reorder these components, and that doesn't change any of the descents except for those that are exactly on the path. So if I restrict myself to the permutation that's generated by the labels on this path, their distribution will be exactly the distribution of the descent bias permutation model with the same parameter value q. So I can observe descent bias permutations inside my descent bias trees, which is a natural reason for us to study the descent bias permutation model along with the trees. Okay. So let's now go to results after this rather lengthy introduction of the models. So what can we say about these permutations? As in many similar contexts, there are some phases depending on how the parameter value q behaves, and phase transitions can be observed. So if the parameter value qn is very small, namely so small that qn times 2 to the n goes to 0, then actually a descent bias permutation is with high probability just the identity. It will just be 1, 2, 3, 4, 5, and so on. This is in a way the trivial degenerate phase. It gets a bit more interesting if I have a similar type of behavior, but qn going to 0 slightly less quickly. Specifically, if I assume that qn decays exponentially, or equivalently the logarithm of 1 over qn behaves like n over c for some constant c, then depending on what c is specifically, there is always some integer kc, such that the number of descents is either kc or kc plus 1. So my model generates permutations that have a fixed number of descents, plus minus 1. So this kind of 2-point concentration is also something that is quite common in the combinatorial context. This is slightly less degenerate, but still rather degenerate. My permutation has only a very small number of descents. So it goes up for quite a long time, has one descent, goes up again for quite a long time, one descent, and so on. But, if this is the case, then it turns out that the first are elements, and this is what I mean by a local limit. I'm looking locally at the first couple of elements of my permutation, and I want to know what their distribution is. So it turns out that in this phase, the first couple elements converge in distribution, and they converge to such a random vector where the x variables here are geometrically distributed, not just x1, this is a typo actually. So x1, x2, x3, and so on all the way to xr. They are all geometrically distributed random variables. So the first element of my random permutation is then following a geometric distribution. The second one is equal to the first one plus another geometrically distributed random variable, and so forth. So I can say rather precisely what the first elements are, what they look like, what their distribution is in the limit. The way to prove this is using some direct counting argument. So a permutation with k descents for fixed k looks as I described it earlier. So it goes up, then goes down in one descent, then goes up for a while, one descent, goes up for a while, one descent, and so on. So it consists of a number of increasing sequences separated by descents. And the number of such permutations is approximately equal to k plus 1 to the n, by the simple argument that any of the n numbers can be in any of these k plus 1 increasing sequences pretty much equally likely. So the only exception is that sort of these increasing sequences must be such that the last one of each sequence must be greater than the first one of the next sequence. But if I just distribute them uniformly, then this is true with high probability. So knowing the number of such permutations, I can also say what their total weight is, because the weight was defined to be qn to the power k, where k is the number of descents, so I get qn to the k. And I need to multiply this by the number of permutations with k descents, which, as I said here, is about k plus 1 to the n plus 1. So the total weight of such permutations is this. I can rewrite this a little bit, and by assumption, my Qn here behaves like n over c. So that's where the minus k over c here comes from. So Qn behaves like e to the minus n over c. The logarithm of 1 over Qn is like n over c. Right. So now I know the total weight of all permutations with a certain number k of permutations. And the function here in brackets is a function of k that has a maximum at either c rounded down minus 1 or at c rounded up minus 1, or possibly both. And for these values of k, this expression here, this exponential, grows fastest as a function of n. And in fact, those permutations where the number k of descents attains the maximum here will be exponentially will have an exponentially greater total weight than all the remaining permutations combined. So this proves that the number of descents is concentrated on at most these points. And for the distribution of the first R elements, one can observe that the probability to occur in the first of the k plus 1 increasing sequences is just 1 over k plus 1 for each of the elements, pretty much uniformly. So I can look at this as a sort of repeated coin flip. I flip a coin that has a probability of 1 over k plus 1 to show heads, and I do this until I get heads. Then the number of times I have to repeat to succeed follows a geometric distribution, and that will be then the smallest label that occurs in the first of my increasing sequences. So this explains the geometric distribution that I mentioned earlier. Okay, so this is the degenerate phase where the Q is very small and my permutations have consequently very, very few descents. It gets a little bit more interesting, maybe, or at least less degenerate, if the parameter q is not quite as small. So if I have qn going to 0, but the logarithm of 1 over qn is sublinear, little o of n, then the distribution of the first r elements in my random permutation will have a limit distribution, but it's no longer discrete. I have to scale and obtain convergence in distribution. The scaling has to be by logarithm 1 over q divided by n, which by this assumption here is actually going to 0. So if I scale with this factor, then the distribution of the random vector of the first r elements of my permutation goes to this random vector where the e's are exponentially distributed random variables. Lastly, if my q doesn't go to 0, but I have a constant value of q, then I can describe the distribution of the first r elements in my permutation by means of a Markov process. So I can exactly say what the density of the first one is in the limit, and then what conditioned on xj, the density of xj plus 1 is. It's given by this. So for each of the x's in my random vector here, the density only depends on the previous one. That's because the bias given by the descents only takes into account consecutive pairs. So it's only the previous element that matters for a descent, but none of the elements before that. So I'm getting this limit distribution as n goes to infinity in the scenario where q is constant or converges to a constant. Unlike the previous scenario, the random vector x1, x2, and so on has a somewhat more complicated distribution. It's not the classical distribution here with the exponential random variables. But still, up to proper rescaling, I can characterize the distribution of the first couple of elements in my random descent biased permutation. So I'm able to provide local information. I can say what the numbers at the beginning of my random permutation look like. For the proof, we need some generating functions that take the number of descents and also the first element into account. So one sets up a generating function like this that encodes all this information. For each permutation, we take q to the number of descents, y to the first element, x to the n over n factorial. This is a tri-variate generating function, although q is more like a parameter than a second variable. And with this generating function, we will be able to obtain all the information we need, because from the combinatorial description, one can actually obtain a partial differential equation for this function s that looks like this. This is well, not too complicated partial differential equation for s. Actually, to be more precise, it's a sort of differential functional equation because I have xy here rather than x. And also the specific value for y equal to 1. Now, explicitly solving this differential equation is possible in some sense, but not very useful. So what we actually need is the derivatives at y equal to 1, because these encode the factorial moments of the distribution of the first element. And we obtain the following result here about the coefficients of this bivariate generating function that characterizes the moments of the distribution of the first element. So the rth derivative at 1 yields the rth vectorial moment of the distribution, and from the rth vectorial moment one obtains the rth moment by a simple argument. So if one has the one, one has the other. And from this particular result, we obtain the rth moment of a suitably rescaled version of the first element of my random permutation. And it can be expressed like this. And we notice that this is exactly the rth moment of a random variable that has this particular density. So it's this constant times q to the x on the interval 0 to 1. And because this random variable with this density is actually characterized by its moments, this allows us to also infer that the distribution of the first element, suitably rescaled, has to converge to this distribution. So for constant q, we obtain that the moments of the first element converge to these moments characterize the distribution, and that gives us the first random variable in the Markov process. And then to get the second, third, fourth, and so on, one sort of iterates this idea. So we can continue inductively to define the other variables of the process. If I let q go to 0, but not too quickly, then I'm in this phase where the limiting distributions can be expressed in terms of exponential random variables. And there it's still a very similar argument based on the same asymptotic formula actually that I showed you earlier. Right. So that was permutations, the local structure of the permutations around the initial bit. I can in principle do this also somewhere in the middle of the permutation and infer similar results. But now I want to do similar things with trees. So I'm looking at the local structure of my tree around the root. So again, local distribution results for these descent bias trees. I generate large trees based on this probabilistic model with the bias based on the number of descents, and then I look what is their structure around the root. And here it's mainly interesting for us to look at constant values of q, because only in that case there is a meaningful local limit. If I let q go to 0 or to infinity, then actually the root degree will go to infinity, and I cannot talk about local limits in a really meaningful way. So I'm keeping Q fixed in the rest of my talk. I'm looking at trees generated based on the bias induced by the number of descents, and I'm looking at the local structure around the root. The first thing there would be the root degree. How many children does the root have? Then how many children do these children have, and so on. So local behavior around the root is what I mean. As a side result, I will say a few things about the path length, which is not a local quantity, but is required as an auxiliary tool in our results, and maybe also interesting in its own right. So similar to the permutations, the approach is based on generating functions. So one can set up a generating function for these labeled trees, incorporating the weight based on the number of descents, and that looks like this. And again, we end up with a differential equation, a partial differential equation in x and q that looks like this. So this can be obtained from the structure of the trees. Basically, I decompose looking at where label 1 is. I take this label away, and then the tree decomposes into smaller trees, which can be translated to an equation for the generating function. And this equation can actually be solved, this differential equation, but only implicitly. So the function a is given by an implicit equation that looks like this. Based on this, one can actually determine an explicit formula for the coefficients of this generating function a, which already is present in the paper of Egesjongler and Remmel that I mentioned at the beginning of my talk. More importantly, we can also obtain asymptotic formulas for the coefficients of this generating function. So this is a somewhat technical lemma on the behavior of the generating function AXQ. So it turns out that this is a rather nice analytic function with a square root type singularity that is very common in the study of trees in general. So when you look at generating functions for families of trees, quite often they have this type of singularity. Yeah, in general, this is something that's very common in the asymptotic analysis of generating functions. Right. And if you have an expansion like this with a so-called dominating singularity, so a singularity x naught with the property that there are no other singularities of equal or lower modulus, then actually one can translate the analytic behavior of the generating function to an asymptotic formula for the coefficients, and that's what we're doing here. Moreover, one can include additional parameters in the generating function, for example, the root degree, that gives us a trivariate generating function with an additional variable u that encodes the root degree, for example. Then looks like this. So as long as q is constant, the root degree has a discrete limit distribution, which one can actually characterize. So the result here is that if I keep my parameter q fixed, I generate rooted labeled trees biased by the number of descents in the way I explained. Then the root degree will follow a distribution in the limit that has this specific probability generating function in U. So Q here is a constant for us. This is indeed, as one can verify, a proper probability generating function of a discrete distribution. One can, in fact, say what the individual probabilities are. So probability that the root degree is equal to k converges to this constant here, depending on q and k as n goes to infinity. So we can say quite precisely what happens around the root if we generate trees according to this descent biased model. It's quite interesting how this sort of global condition, I'm counting all the descents in the tree, and then I induce a bias on my trees based on this total number, has an effect on the local structure around the root that can be seen by this formula. And one can say a bit more. We have what is called a local limit, which means that for every fixed neighborhood, the neighborhood around the root converges to some distribution. So I can fix R, look at what is exactly the tree that I obtain by just looking at all the vertices of distance at most R around the root. And then each possible tree that I can get in this way has a certain probability, and what we are able to show is that this probability converges. So we have a limit distribution for the local structure around the root. This is similar to what we had earlier for the permutations, where we looked at the initial bit of the permutation, and we could say the distribution of the first couple values in the permutation is such and such, depending on what Q is. So to conclude, I want to say a little bit about distances because this was the original motivation that I mentioned. I want to interpolate between, uh, on the one hand, labeled trees where the height is about root n and where distances are of order of magnitude root n, and the recursive trees where distances are of the order of magnitude log n. And the path length is a way to capture this in some sense. So it's the sum of the distances between the root and all vertices, and this is a quantity that has been studied quite a lot. So for this, we obtain an asymptotic formula for fixed q. So the total path length is of order n to the 3/2 whenever q is fixed. If I divide by the number of vertices, I get square root of n. So I'm still in this sort of regime where distances are roughly of the order of magnitude root n. But as q goes to 0, the constant here, the constant factor, as q becomes smaller, this constant factor gets smaller and smaller. Um, so this result in a way captures the transition in the trees getting flatter and flatter, and the distance is shorter and shorter as my q decreases. We are currently busy studying this in greater detail, and I will say a little bit about this on my final slide here. So these are some directions that one can look into further and that we are busy exploring as well. So one thing one can do is look at what is called a mesoscopic limit of permutations. So one looks at permutations not on a fixed length, but in a slightly larger window. And it turns out that in order to see some non-trivial behavior, the right size of window would be like this. Another thing to look at is the geometry of these random trees. So for fixed Q, it's known that, or to be more precise, so for Q equal to 1 for random rooted label trees, it's known that these trees have a continuous limit if I rescale, and it's called the continuum random tree. For fixed Q, this still appears to be the case, and we're currently working out the details of this, but indeed for fixed Q, it's still the same kind of limit. For Q going to 0, further interesting phenomena occur. So if you rescale correctly, you can actually still show that something like this holds even as Q goes to 0. And again, phase transitions can be observed. So specifically when Q is of the order 1 over n, something happens to the structure of the trees. Yeah, this is what I'm also mentioning here. So what can one say about further statistics, quantities like the average height, local properties like average number of leaves and so on? What can one say about their distributions? Are they monotone in Q, for example? So these are still some directions that we are currently exploring and that are certainly interesting. Another thing that one could conceivably do is to change the weight. So here we have biased by the number of descents, but instead of descents, one could also use other things. For example, the number of inversions in trees. Inversions are like descents, except that the two vertices do not necessarily have to be parent and child, but any vertex and any descendant that are sort of in reversed order. This is similar to inversions in permutations as well. So there is still quite a lot to explore around these models. We found some rather rich and interesting behavior, many interesting types of limit distributions. And as I said, still quite a number of interesting directions to explore further. So with that, I would like to thank you very much for your attention, and I look forward to any questions you might have.
Thank you, Stephan, for this nice talk. Please, are there some questions? If you can go to slide 11, please.
Certainly.
Okay. Are there No, 11. Xi, the geometric random variables, Xi are ID or not?
Yes, yes, they're
Uh,
all IID, all geometrically distributed and all with the same parameter.
and we know the parameter. The vari
Yes, it's based on the observation that I made later. So, where was that? So I have this success probability of 1 over k plus 1, that a certain label occurs in the first increasing sequence. And so this 1 over k plus 1, this will be the parameter of the geometric distribution. This will be the success probability for that. And the k is this number of descents that we know to be of constant order when q is in this particular phase.
okay. Thank you. The slide 12.
Slide 12, yes.
Uh, yes, where you have the density. Yes, density.
Density? The density
Density,
comes
density is 12 or 13. Okay,
15.
okay, 13.
Yeah. This density, you mean? Or
No, before,
earlier,
please. Before. Okay, okay. Yeah,
uh,
13.
maybe you mean this one here.
Yes.
This
Okay.
question. Yeah.
Why is this a density? Why it is a density, this function? Q to the power x minus x, j, conditional density. Why it is a density?
Uh, well, it's not completely obvious that it is a density, but you can do the calculation and see that it does integrate to 1. But importantly, the density is conditional. So for each of the elements of my vector, each xj plus 1, the density depends on the previous element.
Okay. The indicator x bigger than x, j, is
Yeah.
for all x or just a factor of 1 minus q?
Um,
The density
so,
is,
so this here is 1 minus q times the indicator function. So
oh,
this 1 plus q is present if x is greater than or equal to xj.
okay,
So this here is 1 minus q when x is greater than or equal to xj, and otherwise it's 0.
okay,
So that's
okay,
what this indicator here
okay.
means.
Thank you. The same slide. Have you
Mhm.
some characterization about the limit distribution of the vector x1, x2, xr? What is the distribution? What is the some characteristics of this distribution?
Well,
At first, a question: are xi here ordered or no? X1 less than x2 and so on. Must be ordered, no?
hang on. No, I don't think so. Uh, no, they're not. So I'm here in the constant phase. So the bias on the number of descents is not that strong anymore. So in the previous regimes where Q goes to 0,
Why?
um,
Yes.
the bias that I'm introducing is rather strong. So descents are punished quite a bit more. But when Q is constant, the punishment for a descent is in some sense less. And so it can occur within the first R elements that I am going down. It's just somewhat less likely, but not a whole order of magnitude less likely. So they are not ordered. The joint distribution of this vector is probably not very simple. The best we can do is this sort of iterative construction where we give the density of the first element and then the conditional density of each of the
Okay.
subsequent elements based on the previous one.
Okay. Okay. Thank you. Are there some questions, please?
Good evening, respected professor.
Hello.
Uh, this methodology is used by permutation methods on trees graphs. Can we use the same methodology on larger graphs like social network graph, like chemical graph? Because this methodology is about permutations.
I suppose you could do similar things, yes. You would
But
have
but
to
there are
you would have to
as
introduce
as
some sort of measure like the descents in this particular instance, right? So the whole probabilistic model was based on this notion of a descent in a tree and then
because
introducing a bias. But please go ahead.
but you know, in chemical graphs or larger social network graphs, there are many cyclic graphs. If when we will be applying this same methodology, can we obtain the accurate result, or it will be about assumptions?
Well, I mean, the model as it is is a priori not really defined in other graphs,
Absolutely.
right? Because this notion of descent depends very much on the tree structure. Uh,
Okay,
but
okay.
but similar probabilistic models certainly do make sense in graphs where you generate graphs at random according to probabilities defined in a similar way, maybe not based on number of descents, but some other quantity. You could certainly come up with many interesting quantities there that could enter a similar model. So it's basically two ingredients that you need for such a probabilistic model. Um, you have some sort of combinatorial parameter, and uh, and then you introduce a bias with a numerical parameter q
Okay.
that says graphs are have a probability that's proportional to q to the power, well, whatever your um, chosen combinatorial statistic is.
Okay, okay. Thank you, Professor. I got it. Thank you.
You're welcome.
Other questions, please?
I have some questions. Can
Yes.
people hear
Yeah.
me?
Yes,
Yes.
please.
Okay. Thank you very much for a nice talk. So, because of the correspondence between parting functions and trees, we know that the unluckiness statistic is equidistributed with the descents in trees. And also, the displacement is equidistributed with inversions in trees. And well, we used to try to couple those two statistics together, but it did not work in parting functions. So I was just wondering, it looks like you have a bivariate generating function for degrees in trees as well as descents. Is that correct or not?
A bivariate generating function for
You have a root
the
degree.
root degree and the inversions. Sorry, the root degree and descents, yes.
So is there an explicit bivariate generating function?
Sort of. I mean, even the generating function that only involves descents is not completely explicit, but it's given by this implicit equation, which I have somewhere. Um, so here, if I just take this generating function with the descents incorporated, then it's given by this implicit equation. And I can introduce a third variable for the root degree, which I actually did here. And I can express the trivariate generating function that I get in this way in terms of the bivariate function AXQ from before. So yes, I can do this. And I suppose other parameters could be incorporated as well, but at the price of getting even more complicated expressions, of course.
Okay, yeah. So this is something I'm looking for. Thank you. Oh, and also I was wondering by putting Q to the number of descents, will that have some impact on pattern avoidance in trees? For example, if you have Q going to infinity or Q going to zero, then you have like 1, 2, or 2, 1 pattern avoidance. Like for regular Q, do you have some expectations on what will happen?
Depends very much on the pattern, I suppose. I think one can already do this with permutations as well. So you bias them by the number of descents and then look at um, sort of the distribution of patterns. But we haven't actually looked into this. I do not know what exactly to expect.
Okay. Yeah, so like this talk motivates me to think about many other things. Thank you so much. Thank you.
That's good to hear. Thank you.
Other questions, please? Can you give some information about how the height is affected by the coefficient Qn, by the parameter Qn?
Great. Yeah, so we do not have such precise results about the height, but what I showed you about the path length essentially tells you what's happening. So dividing this by n gives the average distance to the root. So you have this constant depending on the sort of factor depending on q times the square root of n. And the height is not very different from this. So what you observe is roughly as q goes to 0, square root q logarithm q times square root n is the behavior. So if q goes to 0, then of course this prefactor goes to 0, making the distances to the root shorter. This captures it. But we do not have particularly precise results for the height, unfortunately.
Okay. And have you also some idea about where in the tree we have the maximum of nodes? Where is the maximum of nodes of the tree are located? The depth of the tree where we have the maximum of nodes.
Yes. Well, that depends on Q, right?
Yes.
So um, the the most interesting scenario in some sense is the phase transition that occurs when Q is of order 1 over n. In that case, it turns out that the vertices so cluster at multiples of logarithm n. When Q is larger than this, the distribution of the nodes is more or less the same, except that sort of you have to rescale in the correct way. But for constant values of q, you get this limit you get this limit as n goes to infinity, which is the continuum random tree. And with proper rescaling, you get the same type of behavior, not just for constant q, but actually all the way down to q of order 1 over n. And that's, as I said, where the phase transition happens and the vertices cluster at different levels. But so again, if I just want to say the order of magnitude, it would be this square root of q times logarithm of q times square root of n that I mentioned before. This is roughly the distance of most vertices to the root. So we have a factor depending on q that goes to 0 as q goes to 0 times the square root of n.
Okay.
This is sort of the one-line answer.
Okay. Other questions, please?
Respected professor, are you using any software like machine learning or any other software tool by which you are analyzing the distribution patterns Can you guide us about it, or you are doing without any software for final outcomes? How you analyze the final outcomes of this study?
We were not using any machine learning or any other software here. So the most the greatest extent to which we're using computers is to assist us in some of the generating function calculations and asymptotic analysis. But
Oh, okay.
we
I
didn't
got your point. So you are not using any software. You are just using the simple calculational method by which we can use simple computers or any calculators.
did not apply machine learning or any other advanced computer tools. Also, we did not actually simulate these trees. Would be quite interesting to actually do that.
Yes.
But this is actually not so simple. So to actually generate them for some large
On
value
machines.
and associated Q.
Oh, okay, respected professor, I got your point.
Okay, thank you. Please, if you can go to slide 15, 15.
Sure.
Okay. Here at the end of the proposition, the earth moment is given by some function, which is the earth moment random variable with density is free of R.
Of course, the density is free of R because it's the Rth moment, right? So the density doesn't include R.
Okay.
The density only depends on Q.
Mm-hmm.
And of course, X here. So X is the variable of the density.
Okay.
So you see that the only occurrence of R is actually in here.
Okay. Sorry.
The rest is just the density as a function of X. So this is just how to calculate the moment of a random variable.
Okay, sure. The previous slide, please.
Yes.
What do you have? Yes. What is the function of f pi? Is the first element. What do you mean
First
by
element of a permutation?
Of the permutation. Okay. Thank you. Are there some other questions, please? Other questions? If not, we have to thank again Professor Stephan Wagner for this nice talk. And see you next Tuesday with the talk of Professor Bernard Guidenberger with title An area limit law for the balance of labeled and unlabeled gallet trees. Thank you again and bye. See you next week. Thank you, Stephan.
Goodbye.